Good morning. Welcome to ECE 420, lecture 9. Today we will talk about single stage amplifier, and we will begin today's class by understanding what are the fundamentals of an amplifier and what will be the key questions that we have to ask when you know what you need for an amplifier. So let's begin with the key questions. First question: what is an amplifier? Second, what are the key figure of merits of an amplifier? Figure of merit. Figure of merit is some metric that you identify to compare the amplifier merits. Merit of an amplifier. Third one will be how can you make an amplifier with one MOSFET and one resistor, or a pair of resistors, or few more resistors. Fourth, how can this be improved? Right? These are the main questions that we will have to ask. Now, what is the easiest way, or as in a graph, to understand what is an amplifier? So this is your V in, V out. So when you need a linear graph, that is your V in equal to V naught, your V out equal to V in, this is unity gain, meaning gain of 1, or V out by V in equal to 1. When you mean a gain, you need the gain to be where V out by V in is greater than 1. So how do you measure this? You measure this using the slope, right? Slope will give you V out by V in. Now, if you need a gain, you need to have something whose slope is greater than the unity gain slope. So that waveform will look something like this. Assuming it is starting from 0, the waveform will look like this, or it could look like this, or it could look like this, right? All these are having a slope greater than your system, right? Now, assume you use this graph for gain, right? And you send an input signal to this one. What is this input signal? This is my input signal. So line around which it will go. So I'll give a small input signal here. So this is the maximum and minimum range that you have. Now, if you take this maximum and minimum range and compare to this graph, so this will be another range. So you will see the output between these values. This is the input V in, this is the output V naught. You can clearly see graphically that there is a amplitude increase in V out. So this is what you have to expect out of a gain. So what is the known way of designing this information? We will denote amplifier with a triangle typically. you have the input V in. The output is either seen after a resistor RL, where the value of output is taken between RL and the ground, and you will have a power supply called plus V, and you might have a power supply minus V. Historically, you've got plus minus V, but currently you will see that this minus V will be equal to the ground. Minus will be equal to ground. Now, this is your amplifier definition, how it works. Now, what will be the features of this amplifier? The features of this amplifier will be that first thing is the output will be a faithful replica of input signal. But with an amplified magnitude. Right? Second, your active device will be heart of the amplifier. Will be heart of the amplifier. Third, you will need to have linear characteristics. You have to have linear characteristics to avoid distortion. Avoid distortion or avoid introduction of the distortion into the output signal. So these are the main points that you will have to work with any amplifier. Now, there are, we will go. So how do you represent a signal? A signal can be represented either with a voltage or a current. Now, using this, let us find out what are the various ways that you have working options in this one. So assume you have an amplifier, right? Now in this amplifier, you need to apply an input voltage and you want to get an output voltage. So what would that be? So how do you apply an input voltage? You'll apply a DC voltage and a series resistance, right? This will be RS and V capital S. Now with this input, you have got two kinds of outputs you can give in this one. So one, you can get either a voltage output, V out, which is the resistor RL, right? So you have plus or minus, or you can do the same thing with a current output. So voltage in, and then you will get a current out. Same RL, only thing is the current is now flowing into the device, right? Now, this is called a voltage amplifier. And what is this called? Because input is V, output is V. In this case, it is called input is V, output is I. So here you will get a voltage by voltage output. In this case, you will get a current by voltage. Now, what is current by voltage? Conductance, right? So this way it is called a transconductance. It is a transferring. So transconductance amplifier. Okay. Now, you can do the same thing with respect to the voltage amplifier by giving, now that you have given both inputs as voltage, the next option is give both inputs as current. This is there. So how do you give a current source? A current source is given with IS, current source with a parallel resistor. Now when you give a current input, let us copy this current input for both of them. So when you are giving this current input, there are again only two things you can see. One, either take it at the output or take it at the input. So we'll just copy this one here. So you'll have a resistor output or a current voltage output, or you'll have a current output. Now when you have this way, so this is I. So in this case, your input is I. What is this called? This is an impedance. So this is called a Transconductance Amplifier. Okay, this is commonly used in optical circuits, and they will be used called TIA, optical drivers, or high-speed circuits. TIA is needed a lot because you will have a lot of small current input. You need to multiply to a very large voltage output. So you will use a lot of TIA in those conditions, right? Transconductance amplifier will be used in an op-amp, operational amplifier, and this where you need to convert the input voltage difference into a voltage current difference. So you will do a delta V to delta I. Then using current amplification techniques, you will times excuse me, you will make it K times delta I. Okay, now you got a very large current difference for a very small one, and then you will finally convert this into a delta V. So you'll end up getting K times delta V. Okay, so this is also another trick you will use. Now what is this one here? You have got I over I. I over I is a current buffer, or you would simply say current amplifier. So using only the voltage inputs and the current inputs, we have found four combinations where you have got voltage amplifier, where you do a voltage over a voltage. You have a transconductor amplifier where you are current over a voltage. You have a transimpedance amplifier where you have got voltage over a current, and a current amplifier. So these are the four basic amplifier configurations, whether it is single-ended or differential-ended, that you will have, or a single stage or a multi-stage. So this is a basic understanding. Now, what are some of the more practical characteristics? Practical characteristics, what you will see is, you will see if you are, it's called, I would rather call practical, I will call it realistic transfer characteristic. Now this realistic transfer characteristics is highly dependent DC operating point of the system, because you can start clipping, right? Either if you give the voltage input like this, if you give the voltage, now depending upon where you are taking the output, if you are taking on the higher side, if you have a equation like this, where you are on the higher side, your voltage can start clipping like this. This is called high side clipping. Okay, this happens because it is saturation on the high side. Now, sometimes you can have clipping which is happening on the lower side. Which is called low side clipping. And this is happening on the saturation is happening on the lower side. Now, why this will happen? This happens depending upon where you choose the DC operating point. For example, in this case, the DC operating point might be here, or it would be on the lower side. In this case, it would be on the center. In some cases, it could be on the upper side. So depending upon where is your DC operating point, at that frequency or at that operation, your clipping might come into picture. So this is a very realistic scenario. So here are the features where you will call amplifier saturation. You will encounter this commonly. And how do you avoid them? Second, it will limit your signal swing. Right? Because it is clipping, it will limit your signal swing, both input and the output. And finally, your swing depends upon the DC bias point which we mentioned. So when you are going to do your simulation, which you will probably begin after this class, you will see. So this DC bias is also called quiescent QUIESCENT, quiescent point. This is alternatively also used as DC operating point also. So these are the things. Now, other desired features. There are many desired features that you need to have. And this is where a lot of activities happen. So first one is low power. This is always an innovative area. You can always get a lot of new items here, right? Second, wide frequency response. This is needed when you are working with wideband signals, right? Whose have a bandwidth, whose bandwidth is very large. So typically we would define this bandwidth to be greater than 100 megahertz. Would be a wide frequency response. So you will have designs centered across a particular frequency. This frequency say is 1 gigahertz. So your wideband would be 50 megahertz on each side. So the bandwidth will be starting from 950 megahertz to 1050 megahertz. This is one kind of a bandwidth. If you go towards the RF section, you will have, for example, this is 10 gigahertz, and then you will have a bandwidth of 1 gigahertz on each side. So it will start from 9 gigahertz to 11 gigahertz. So this is also wideband, and this is also wideband. But you have, they are wideband in context. You will see this kind of a wideband signal more in wireless operation. You will see this kind of a wideband in wireline operation. Or now in the recent past, you are going to see in your 5G, 6G kind of a scenarios where you are going into a wideband. Another one is terahertz range. We will again see a wideband. Another one is the 66 gigahertz range, radar range where you will work. Another is the 10 gigahertz radar. This is a 10 gigahertz expand radar. expand radar frequency, this will operate. So there's a lot of applications of wide frequency response. Next, compared to all of them, you have to be extremely robust to process variation, process voltage and temperature variations that you see. Last one is they have to be inexpensive. When we mean inexpensive, the count of the devices that you used has to be lower or as minimal as possible. Whether it is an external usage or it is an integrated usage as an integrated circuit, or this would be discrete circuits. Everything has a cost associated with it. So these are the realistic transfer characteristics that are needed to understand. Now let us convert this into MOS devices, right? How are they going to be represented? So this we will call, this section of the content, we will call it as Cmos amplifier configurations. So what this means is, how can you use the CMOS device to configure various ways? So there are two ways of doing it, right? Or rather 3 ways. What are the 3 ways? You can connect the input in a MOS transistor in 3 places. So this is 1, 2, 3. So where are the 3 places? You can apply it at the gate terminal, source terminal, or the drain terminal. So you will have V in here. You apply it at the gate terminal. Another one is you apply it to the source terminal. Another one is you apply it to the drain terminal. Right? So these are 3 ways. Now, where do we take this is where you can connect the inputs. Now let us connect the outputs. So where all can we connect the outputs again? So the most common one that we will observe is at the drain. So you can connect the V out here. Next, we can connect it at the source. V out. Lastly, we will connect it at the gate. And typically we do not write like this. So we make it a habit that voltage input is always written on the left hand side, and you will replace this there. Now, why do you say this? This is just a convention to understand that we train our minds that we will look in this way. This is not the absolute way. So let us start naming them. A, B, C, D, E, F. So these are the common thing. Now here with this you can start among all these combinations, you can now define what are the various connections that you have. So if your input connection and amplifier type. Now, if your input connection is given at the gate and taken at the output is taken at the drain, if your input connection is A and D, then you have common source amplifier. Okay. Next, if your input connection is again A and you're taking the output at E, right? What is the common here? Is gate is where you are giving the input, source is where you are taking the output. So what is this called? This is called common drain amplifier. Next, what happens if you give it at which is here B? If you give the input at B, what will happen? You can either take the output at the gate or you can take the output at the drain. So what are the options you have? B and D, because you're taking the drain at the output. Now what is this called? This is called a common gate configuration. Now there are many places that you will not use this. First thing is, you may not use output taken at the gate. It is extremely rare, since this is a gate controlled device. Most of the time gate is taken as the input, right? So gate output you may not use. So this option F is not used. Another option you will rarely see, I said rarely, it's not that impossible, is C, that is input giving at the drain, right? Typically drain is used as an output. So you will not see option C being used. Now coming with the source, right? Source is one place where both input can be given and output can be taken. So you will actually see source appearing in both configurations. Okay. So you have B, which is source at the input, and E, source at the output. So you will have, these are the common configurations, and these are the functional ones, right? The commonly used functional items would be this one. Functional options are these. So in this case, you are only seeing the voltage configurations only, right? So all are voltage based configurations. Any doubts? Now let us jump into the first of the units. First one is common source amplifier. Now what happens in a common source amplifier? The input is applied to the gate, output is taken at the load. Now why is this called? Because as we explained some time back in the 2 classes before, source terminal is common to both input and the output. And the easiest way of representing this is as follows. So it's going to be your VDD. Here is going to be your VSS. This is your output. This is input. And if you see, the minus for both the output and input is VSS. So this is a common. So that is why it is called a common source amplifier, where input is given at the gate and output is taken at the drain. Now, what is a typical way of giving an input here? You will have a DC circuit and a current limiting resistor or bias resistor in some cases. And this will typically form the signal source. And this is connected to VSS. Next would be the ground that you will apply. The output you will take it either across a resistor or you will take it across a capacitor, depending upon the case. So the current flow is, this is going to be IR, this is ID, this is IL. So your KCL will always result that current to the resistor is always ID plus IA. So this is one thing that you'll have to understand. And this we will call it as signal load. So this is your signal source, this is your signal load. Input applied at the gate, output taken at the drain. This is called a common source amplifier. Now, what is the large signal analysis we have done? We have done the large signal analysis for this many times, and let us refresh. So this is V in, this is V out. And we have seen that this characteristic is like this, where this is going to be your V threshold voltage in the cutoff region, right? Then you have the input will come here, where this is going to be the linear or triode region. This is your saturation region of biasing. Okay, clear? Now, how do we use this? What is the small signal gain and the large signal gain that we have found out? We know that if the GM value is given as mu n Cox W by L times VGS minus VT. What is VGS? Vn. Vn minus VT is what we call as the GM. So this is the small signal gain. Now, what is the output that you will see? The output that you see is multiplied by this resistor here. So the gain is given as, because the internal gain, right? You see, this is the small signal gain. If you recollect, this drain node, the resistor is connected to the ground in the small signal part after GM VGS. So the AV will be GM RD. And if you remember, the sign is going to be negative. There is an inversion that is happening. So gain is going to be GM minus GM RD. So what you will do is a very small voltage change at the input, dV in, will get into a very large voltage change to be dV out or dVL. And this gives you what is the delta change. And the output is given as input is delta V in, V out will be minus GMRD delta V in. If you take the ratio between the two, minus, you get minus GMRD. How do we get minus GMRD? This is GM VGS, right? Now VGS will be translated into the voltage. Voltage is delta V in. So GM VGS multiplied by the RD. So that would be your output. So this is the large signal analysis. Now, let us do the quick small signal analysis just to confirm what we did orally. So GM VGS, we will draw now the, assume we have drawn the gray terminal, gate on the left, drain on the right, source at the bottom. So you will have the gate terminal coming here, which is V in, and the common source terminal that we have here. So this will be your plus, minus, and VGS. In this VGS, what is this VGS here? This would be this V1 terminal. So V in is, this is V in, this terminal is V1. So you'll have, this is equal to V1. Now what do you have? GM VGS. GM VGS, and you have R0. Since there is lambda is not defined, if lambda is equal to 0, we will take R0 equal to infinity. So that R0 will be removed. What is pending is RD. Right? This is RD. And here you will have the output taken here. Now once this is there, What is the current looking into the circuit here? What is the current here? I from the L, that will be minus V out by RD. That is the current that is going into this node. So if you apply KCL here, the current branches off here and goes back into this. Now, what does this become? This GM VGS becomes GM1. So if you apply KCL at this node, let me use a different color. If you apply KCL at this node, you will get GM VGS is V1. GM V1 is equal to minus V out by RD. So you can say V out is equal to minus GM RD V1. Now V1 is your input. You bring it down here. You will get minus GM RD as the gain. So this is how you apply the gain. Right? Now, what is the input impedance and output impedance of the circuit? Right? What is input impedance? This is an important, you will get combinations of input impedance, output impedance as your gate questions. So you will know that. So what is input impedance? Rin. Input impedance is given as, okay, how do you do that? Give a test input signal, right? Test input signal, Vx, it will have its own current, Ix, right? If you remember, this is going into the drain, right? So Rin is Vx by Ix. If you remember, the current going into the gate of an amplifier is, or gate is 0. So Vx by 0 is always infinity. So Rn will be infinity. Remember, if the input is given to the gate, it is always infinite impedance or extremely high impedance. Now, what will be the output impedance? You will apply the same test voltage at the output. Vx, Ix. So output impedance also is Rout equal to Vx divided by Ix. Now what does that give? What is the Vx that you're seeing? V out. What is the current that you're seeing? Minus V out by RD. So if you equate that, you will end up with RD being the output impedance. So whatever is the drain impedance that you see, that will be the output impedance that is present here. So this is the total impedance that is observed. So let us now find out if there are any observations, right? These observations are important. So like previously mentioned classes, gate, midterm, finals, this is all reference everywhere. So what are the observations? First one. First observation is your gain. Your voltage gain is minus GM RD. Right? Now, what does this mean? If the gain changes due to the input, what do you get? Now the GM is defined for small signal. Always remember, GM is defined for small signal. If the input signal goes larger, then we'll act for large signal. If your Vin goes up, then it becomes a large signal. So then it becomes a large signal component, and your swing also will go up. This is the first observation. Second, this as your input signal goes up or your gain goes up, it can lead to non-linearity. Okay, this is both good and bad. It is good when you want a comparator behavior, right? When you actually want it to be a non-linear behavior. It is bad for an amplifier where you want it to be linear. So choose one. So if you have a very high voltage gain, the system will act like comparator. So you have to ensure that you maintain the gain of an amplifier by controlling its DC operating point. Okay. Third observation. How do you minimize the non-linearity? If you want to minimize non-linearity, you have to minimize gain, right? If you want non-linearity to be lower, your gain has to be lower. For gain to be lower, your GM has to be lower. Your GM has to be lower. What does that mean? Your transconductance is weak. You will use a weak transconductance. And to implement this, the DCOP point where you are doing the design and the layout, you'll have to be critical. You have to play a very important role here. Next, how can you increase the gain? Your gain can go up by making GM go up or RD go up. GM can go up if your W by L is up, right? Or by reducing the current, because current comes in the numerator. All the other fixes, no, the current comes in the denominator, right? For GM. Third, now there is a dependence problem here. Dependence comes here. If your W by L goes up, your capacitance will go up. Your inherent capacitance will go up. And inherent capacitance, when it goes up, you will need to have a higher VRD. Papa. And this higher VRD will limit the voltage difference. It will limit the voltage swings. Right? So these are the 5 observations that we have when you're working with a common source amplifier. In addition, what happens when you randomly increase RD, saying you want to get a very high gain? What happens when you increase RD? When you increase RD, Papa, you will see channel length modulation will come into the picture. Okay, and this one, because of this, you will see modulation and the output voltage will reduce. Output voltage will reduce by a factor 1 plus lambda VDS. And this output factor will be critical. Eventually, it will reduce the gain. So how does the gain get reduced? From AV is equal to minus GMRD, right? It becomes AV is equal to minus GMRD. And because you will now form a loop there, so 1 plus RD times lambda ID, right? And this effectively becomes AV is equal to minus GM. Now the role of RD gets replaced by what? A parallel resistance R0 and RD. So R0 plus RD divided by, sorry, R0 RD divided by R0 plus RD. Okay. How can you see this? This effectively lowers the gain. This can be easily visualized in your small signal analysis. So this is your GM VGS. This is VGS. This will be R0, right? Now here will be your RD. This is V out. This is V in. Now if you see, R0 is connected to the ground, right? So R0 is also connected to from same node to ground. So RD is connected from same node to ground. So these two will come in parallel. So you have R0 in parallel with RD. So you always know that whenever anything comes in parallel with a resistor, it assumes the value of the lower value. So it becomes R0 parallel in RD is less than RD, no matter whether R0 is more or RD is more. So your gain also will come down. So the having a very large RD will introduce VDS, and VDS will introduce a lambda. So also having a very large RD is not appreciated if you want to keep the gain high, right? That is why you reduce the factor by R0. And here R0 is given as 1 over lambda ID. See, if you want to reduce the ID, your lambda channel length modulation comes into picture, VDS comes into picture. Eventually, you end up with a lower gain. So this is why in the assignment question, I asked, is channel length modulation beneficial or not? So in sometimes yes, sometimes no. Right? Now with this, we will try and see what next do we do. Right now, let me take you to a really realistic transistor, which we have already seen in the last class. Realistic implementation of a common amplifier, common source amplifier. Okay, now we will always start with the active device. What is the active device for us? The active device is the NMOS transistor. Right, now you have got the NMOS transistor. With this, you would now like to apply the bias condition. Now you will have an DC bias coming or AC bias, V signal. You have the resistor here, source signal resistor. Now you do not want any DC signal to get transferred, which will impact your bias condition. So you block DC. Block DC capacitor. After you block the DC, you need to now bias it at your DC OP. Bias at your DC operating point. For that, you will use a external resistor, right? The RG. So now this RG will help you bias your point. This C will help block the DC voltage and take forward. Next is your load resistance RD. You do not want the DC of this block impacting the next block. So you will now block the DC again. Right? Then you will tape the small signal output here, which is V out. You will tap this across the resistor RL. So this is your load output. This is your input. Now, another thing you need to control. So what is your control factor? You can put a current source here to control the item. Control the common source amplifier. And here you will also have a bypass capacitor. Right? Now, this typically looks like what is your activity. Now, let us call it out. So, this DC blocking capacitor, what is the other name for DC blocking capacitor? It's called coupling capacitor. Okay, coupling capacitor C1, coupling capacitor C2. What does this do? Blocks all DC plus small frequencies to getting into the gate, so that the gate doesn't get modulated from the previous stage that you're using. So for example, if you have 3 stages connected to each other, stage 1, stage 2, stage 3. Now each one has their own DC operating point, DC1, DC2, DC3. So how do you visualize it? Assuming this is the DC point here, assuming this is the DC operating point here, assuming the DC operating point here. Now, if these two get connected to each other, right? If these two get direct, then there you will see voltage division here. And because of this voltage division, either stage 2 impacts stage 1 or stage 1 impacts stage 2. Both will be there. So to avoid that, you put a blocking capacitor here. You put a blocking capacitor so that DC doesn't impact here. You put a blocking capacitor here, you'll go. So this is called a blocking capacitor or a coupling capacitor. So these are the two coupling capacitor. For example, if you are in stage 2, you need one coupling capacitor to avoid stage 1 here. So that is here at the input side. Now you don't want stage 2's DC to impact stage 3. So you put a blocking capacitor here. So these two are taken care of, blocking any DC. So now whatever is coming here, whatever is the voltage that you see here, will come as a drain voltage at the output. This is the load resistor. What is load resistor? Load resistor is equal to only to take what is the amount of load that is present. So it could either be RL or it could be a placeholder. This is what you will typically see. This will be a placeholder for next stage. For example, you have stage 3, the impedance or the load of the stage 3 gets mimicked here. Okay, it is only mimicked. It is not exactly there. So it's a placeholder. The generic term to be added here is impedance. Excuse me. Excuse me. So you will be impedance Z. So you will typically call it as a load impedance, because your load impedance can be resistive, it can be resistive and capacitive, it can be resistive, capacitive and inductive. So you don't know which combination it is. So generically you will do impedance and call it as a load impedance. Next, what is this? You need an ideal ground here, right? For this to function. For that you provide a short. So this is called a bypass capacitor. What is this bypass capacitor activity? It basically takes all the small signals, right, and shorts them, right? All the small signal references, at the high frequency, all the high frequency signals get shorted. They get shorted, and all the low frequency plus DC get blocked, or it is open for them. So this is why you bypass the light signal frequency or large frequency signals, such that they don't operate or impinge the operation here. And this is the load source resistance that you current that you have here to refer. Now, what are the any questions that you have based on this before we go into the small signal operation. So intuitively, let's now find some intuition, right? GMVGS, R0, VGS, right? Now, what are the additional components that you have? You have a DC blocking capacitor. So this we know will not impact block. So only RD is pending here. You connect it to the source. And at the source, you have the current source. So it is open. You have the capacitor, so it's open. So it is effectively shorted at the source itself, at this terminal. Next, at this input, what do you have? Input, you have this resistor here before the DC blocking. This is RG. And if you remove this short, you have the RS and the input source. So this is the small signal equivalent of this circuit. Now, we have drawn the voltages. Now let us draw the currents. What are the currents that we will have here? You will have the IRL and this will be ID. IRL is negative, ID is positive. Correct? Next, you will have source. Source, there is no source current here. Next, gate. There is no gate current here. So whatever current goes here has to flow through this RD. So this is your I input. Now, after these two, you will need to know the input and output impedances seen. So what is the input impedance? This is input impedance R in, and here is your output impedance R out. Okay. So now we need to calculate R in, R out, and ID. So this will be the realistic operation. So what happens here? Input current that we know. Now what is RG? Are the input impedance. Can somebody unmute and tell me what is the input impedance? Come on. Okay, let me call out people. Arvind? What is the input impedance, Arvind? Farah?
Yes, sir.
What is the input impedance, Farah?
Rn.
Rin is the input impedance. So what do you see is going to be the Rin impact here straight away? Rin is exactly where Rg is sitting, right?
Yes,
So
sir.
Rin is Rg. Okay. Now, what is the V in? This is the V in, but what is the VGS value here? We will call it as V1. So what is V1 equal to, or Vi? Farah? What is Vi?
Sir, Ig is 0 above, so that Rg into Ig.
Rg into Ig, or you can call it as a voltage division, right? Just think the circuit is like this, right? This is Rg, or we will call it as Rin now. And you will have Rs, and then you will have the voltage source Vin. So this is Vi. So what is Vi? I think this one everybody knows, right? Farah, help me finish this quickly. What is Vi?
So Vn into Rs by Rs plus Rg.
Perfect. So this will be P in into Rs by.
Yes, sir.
No, you are taking the voltage across here, right? So
Okay, yes, sir. Rg by Rs plus Rg.
Rg plus Rs. Very good. Geetika, you are next. So what is the output? What is R out? Geetika, you there? Nobody is there. Okay. Who else is there? Only 10 participants today, half the class. Okay. Vani, could you help me in this, Vani? Can you help me in this? What is R out?
R is do we need to consider RD also?
Yes, you need to consider RD.
RD into ID.
RD into ID? No, I'm asking R out. Output, what is the output impedance that I see here? Kajal? Can you help Kajal? What is the R out? Lasya Priya?
Yes, sir.
What is R out?
So we should be considering both R0 and RD.
Correct.
So,
So what will that be?
I think R0 parallel to RD.
R not parallel to RD. Very good.
R0 RD by R0 plus RD.
Correct. Now, what would be the gain in that case? We know what is gain, right? Gain is given as voltage gain is minus Gm RD. But what is this in this case? Okay, let me help you with the answer here. Sai Chandana and Hema Harshita, what is the output voltage? V out. V out is seen here at the output of RD. And the output of RD, you have RL also. Okay, so what is V out? V out is given as, what is this current here? GMVGS, right? So this is negative GMVGS. Now what is the total resistance? You've got three resistors in parallel. R0 parallel with RD, parallel with RL. This RD is at the drain, this RL is also at the drain, R0 is also at the drain. So all three get parallel, right? So what is the actual gain? Gain is given as V naught by V in. V out by V in. That is minus Gm VGS. What is VGS? V in. Go below. So this will be R0 by R out parallel with RD parallel with RL. What is the input? Vi, right? So that is V in by RGS. What is it? Rg divided by Rg plus Rs. So this, when you rearrange, correct? Is this correct? It's wrong. This is wrong. You see the gain Gm AV, right? So what is the total gain? Is Gm times Ro in parallel with Rd. So now you will get the total gain to be, total gain is from V in to Vi. So this is a gain factor, right? We have only said till Vi here. Now if you need gain from output to input, gain V out to V in, then you will have two portions. One portion is this much. This is the second portion. So what is the first gain of this stage? Rg by Rg plus Rs. That multiplied by minus Gm times R out parallel with Rd parallel with RL. So this is the total gain of the system. Right? There is a voltage division here. So you need to account for that voltage division also. That is also part of the gain. Understood? So these are the practical implementation, right? This is how it will look like. Now, what happens when there is distortion? How do you introduce distortion here? Where are the ways you can introduce distortion? Distortion can happen when there is extremely large signal coming. So what we can do, we will replace V in with this signal. So if we make V in equal to 4 volts plus V in of t, add a DC voltage also. And what do we call Vi of t? Let us call Vi in of t as a V in V1 cos omega t, sinusoidal signal. Right? It is a sinusoidal or a cosine signal that you can take. You can put this as that. Now let us make what is a V out. V out will be the DC signal VDS plus V out of t. Correct? But we know V out of t is equal to gain times, okay, Vi of t. So remember these two equations. V out of t is gain times Vi of t. Now what will happen? What is AV here? To understand what is AV, V naught by Vn. Let us add a few more variables. So we got V out Rd. Let Rd equal to 5K. The mu and Cox W by L value, let it be 0.25 milliampere per volt square. Right? Then let the threshold voltage be 2 volt. Right? So we have seen this diagram. Okay, let me, for people who are not able to visualize, let me draw it this way. This is Vi. This is plus 4 volt. This is Rd, 5 kilo ohm. Supply voltage 15 volt. V out is VDS. This VDS drop plus V out of t. So this is your circuit. Now this circuit has got this feature. Now let us find out what is the voltage gain. AV. AV is equal to V out by V in. Small signal AV. What is that value? Value is -5. How did we get -5? That is your assignment. You will do and come back and tell me next class. Now, if this input is Vi is V1 cos omega t, what will be the output? Replace Vi output here. So your output will be -5 V1 cos omega t. So this is your Vout. Now, this is the small signal voltage. What is the actual signal voltage? Actual signal voltage V0 is VDS plus, in this case it becomes minus 5 V1 cos omega t. So that is the actual output voltage. So you will see a DC plus some sine voltage there. Now what is VDS value? To find out VDS value, you need to find ID. What is ID? In Cox W by L. Correct. In Cox W by L is how much? 0.25 milli into VGS minus VT. How much is VGS at V equal to 0? V is 4. 4 minus 2, 2. 2 square is 4. 4 multiplied by 0.25 will give you 1. So this is 1 milliampere. So what is the voltage drop across RD? 5 volt. How is it 5 volt? 5K times 1 milliampere is 5 volt. So what is VDS value pending? 10 volt. V0 value is 10 minus 5 VI cos omega t. So this is your actual output signal. Now in this output signal, what is the maximum and minimum? Max and min. So for a cos signal, what is the max? Maximum amplitude is 5, right? Plus 5. Plus 5 V1. Negative is going to be minus 5 V1. Correct? Or this will be the maximum input in saturation region. Now, the moment this device goes out of saturation, it will go into the triode region. And the moment the device goes into triode, this ID equation will fail. So ID equation will have channel length modulation incorporated. So you will have some other value as ID. So your VDS will constantly keep changing. So if the total output voltage becomes very small, then the MOSFET will be in triode. If the total input voltage becomes too large, then the MOSFET will enter cutoff. Right? How can V0 be more? When can V0 become 15? V0 can become 15 when ID is 0. When is ID 0? ID is 0 in cutoff. So when can V0 become very small? When ID is very large. That means the drop across RD is very large. When drop across RD is very large, drop across VDS will be very small. So it will become into triode region. So intuitively, always remember this graph. This is your output, this is your input. Now, if the Vi cos omega t, V0 becomes very large value, that is, this drop becomes very large. When will this drop become very large? When drop across this is very small, or over very large amount of current is being pulled, so swing will go up. In that case, when your Vout becomes very large, what happens? Your device is in cutoff region. Okay. Now, what happens when your device, when ID is very V0 is very small, V0 is very small, means RD is very large. So because RD is very large, this voltage will get pushed, VDS voltage will get pushed. That pushed, you will be in the triode region. So how do you reach this? So VDS is small. This VDS is large. When VDS is large, ID is 0. So whatever is there at the output, it will come, whatever is there at the supply will go to the output. When ID is small, ID is going to be large. When ID is large, it is get pushed because VD, which is the IDRD, becomes more. As IDRD becomes more, the VDS will become small, and this will give into cutoff region, triode region. So this is triode, this is cutoff. Okay, this is your nominal operating range. So you ensure that you are always in the green region. This is your nominal operating range. Any questions? Now let us add some math to it. Okay, I will reuse this equation. What is V out? V out is 10 minus 5 Vi cos omega t. V out is equal to 10 minus 5 Vi cos omega t. Now, what will happen here now? How do you find out what is the min and the max? The secret is, what is the VGS minus VT? VGS minus VT. VGS has DC volt 4. VT is 2. So what is left over? 2 volt. This confirms that VGS is greater than VT. So device is on. It is not in cutoff. So what happens? So for what is the minimum saturation voltage it has to maintain? VGS minus VT. So for saturation, the total output voltage, right? P out, total output voltage should be larger than VGS minus VT value. And that value is given as 2 volt. For anything less than that, it will go away. Now let us use this equation and see what is the maximum input that you can have for staying in saturation. So what is the Vi max? So 10 minus 5 Vi cos omega t should be greater than 2 volt. Then you will get max input. You will get max input in this case. So how do you equate? What are the equation you will have? So 8 is greater than 5 Vi cos omega t, and Vi cos omega t should be less than 8 by 5 is 1.6. Right? So this is the condition you will get. Now, what is the maximum amplitude? Modulus of Vi cos omega t, right? Modulus of cos omega t is 1. That is the magnitude larger. So therefore, Vi, maximum Vi value can be is 1.6. You cannot go beyond that. So 1.6 volt. Now, if the input, now what is the supply voltage for this one? Your VDD in this case is 15 volt. So for an input VDD of 15 volt, the maximum VI it can go is 1.6 volt. Otherwise, your system will enter into the dreaded triode region. You do not know, a lot of things happen. And triode region is where distortion comes into the picture. Okay, so this is one kind of a problem statement. Now, what is another problem statement? The drain current, what is it? The drain current must be greater than 0. Right? You know, when cutoff and this one, it will be devices on. But drain current should be greater than 0. Otherwise, it is going back into the cutoff region. Cutoff region ID is 0. So ID equal to 0 can be both triode and saturation. Correct? But now we will focus on saturation only. For saturation, what will be the ID? ID value will be given as VDD minus R0. Simple, at the drain resistor. What does it look like? Let me reuse this. Just so that you understand why the calculation is happening there. We will use this for reference, right? So what is the current I that is flowing here? This ID is defined as Ohm's law, 15 volt minus V out divided by 5K. Correct? Now this is going to be ID. What does this, how does this define? If you want this to be greater than 0, ID, if it is, this has to be greater than 0. So that implies 15 greater than V0. So whatever said and done, your V0 has to be less than 15 for ID to be greater than 0. This is simple, right? That means you know the upper threshold. You found out what is the upper threshold, and this upper threshold is given as VDD. That means your maximum above limit is going to be VDD. We found out here the minimum V out has to be 2 volt. Let me call this as range minus. Let me call this as range plus. So I like to define the range as follows. If I define the range to be like this, this is the full range. This is 0. This is 15 volt. Okay. Now what is a range plus 15 volt? What is range minus? Range minus is 1.6. So this box represents the range in which V0 has to be for ID to be greater than 0 and this be in saturation. Okay, so this is the upper limit or the ceiling. So some people call this as a floor and ceiling. Understand? No, this is the floor for this range. Now, what is the total voltage? Let us bring back. What is the total voltage equation here? Total voltage. Total voltage is given as V naught of t is 10 minus 5 Vi cos omega t. Now we realize that this value has to be greater than 15. Okay. Then what will happen? Let us find the value of Vi cos omega t. How much is this? Vi cos omega t. Vi cos omega t will be greater than 15 minus 10. 15 minus 10 divided by minus 5. What will be this value then? 5 minus of minus 5 is 1 volt. So the maximum value of Vi cos omega t is 1 volt. Now, since maximum value of cos omega t is 1.0, then maximum value of Vi cos omega t will also be equal to 0, or sorry, will be equal to 1. So that means your Vi in all conditions has to be less than 1 volt. And this is where your definition comes of the R. So if you understand, if you look at this, your Vi can be from 0 to 1.0, whereas your V out can be from 1.6 all the way till 15. Understood? So this would be the range, how you can calculate what are the maximum input swing and maximum output swing of this device. Now, what happens when Vi goes greater than this? You will enter triode region. And there is a small range, 1.0 to 1.6 is a small range, right? That is no man's land. You don't know where to go. But even if you go there, then you will start distortion. So what is a distortion? Your distortion will begin if Vi greater than 1.0 or 1.6 also. So some margin you will have, right? You will have some margin to use it. But what happens when Vi is between these two regions? Vi is between 1.0 and between 1.6. We know that this is triode region. You know, other is saturation region. But you have not realized that there is going to be a cutoff region. Right? So in this range, your Vi enters cutoff region. This is totally nonlinear. Your distortion will be too much. So you should not operate your Vi between 1 and 1.6. Okay. So these are the two operations that we have. So how do we now define the ranges? Now we have ranges, right? 1.6. We have Vi is less than 1.0. Vi is between 1 and 1.6. Vi is greater than 15. Now let us see how the waveform looks like in that range. Let us use our famed gray box. Right? So the gray box has a minimum value, maximum value. What is this minimum value? Vg minus Vt. What is the maximum value? Vdd. How much is this value? Vg minus Vt is 2. This is 15. Right? This is for the input side. Right? We defined, right? Range min and range max. So range min and range max, you will get your V out. Where is your V out? V out is designed at 10 volt. You plot V out in this side and time on this side. So your V out waveform will look as along this volt, 1 volt above and below. Right? We saw that V out can go maximum is -1 Vy cos omega t. So that is, this will be 9. And here will be 11. So this is your condition where Vi is less than 1.0 volt. Now let us quickly draw another graph. We'll reuse this one. Right? So in this case, what happens when you increase the Vi? If your Vi is greater than 1.0 but less than 1.6, what happens to this waveform? Let me try if I can get some animation. This waveform will slowly stop going upwards, right? And will start clipping. So start clipping like this, and this 10 volt mark would have moved here. So this will be your new waveform. So start clipping here. We told, right? Saturation. Saturated output. High side clipping. Now this will be, which area is this? This is cutoff. Right? In this cutoff you will see, so this will be distorted output. Okay. It is going to exceed because you are going to have a higher gain. Now what happens when Vi is beyond 1.6? What happens when Vi is greater than 1.6? You will see a unique phenomenon. When you give very large input, your minimum and maximum both are going up. So you will see extremely large gain, right? We said you will see clipping on both sides. So the gain is going much larger. Rather than just going one side, your gain is going much larger on both sides. So this is called clipping, and this is called fully distorted. Right? This is your fully distorted case. So this is when you call saturation. In saturation region, where it can act as. So when is it in saturation? It is in saturation when it is around the center. Then momentarily it will go into cutoff. After it exits cutoff, then again it is back into saturation. So you will have complete value here. Understood? Now this is again dependent on two items. So there is dependency. Let's talk about the dependency. I'm introducing variables slowly. What is the dependency? The first dependency that you will see is load. Okay. Now, where all can the load come? Load can come on the input. Load can come on the output. So this is called input and output loading. So how does this load get affected? Let us bring back this graph. So all these swings we were telling is applicable here. Now what will happen if I add another resistor at the output? RL. Now what will happen? You will see a resistive divider here. So you will see RD is going to come in series with RL. Large signal, not small signal, large signal. For large signal, this will be voltage division. So your voltage division will happen and your Vout max will come down. And it will come down by how much? Your Vout max will be given as total VDD, right? Divided by what is the load? Max VDS value now. RL times RL divided by RL plus RD. So this is now your new VDS. It is a reduced VDS by itself. So your output going upwards is limited, meaning this VDD blue line on top has now come down. What is it? This blue line has moved down. So this is upswing reduction. Nothing has happened to the lower swing. So you will typically have, this will be your new Vmax, Vout max. Nothing has happened to the ground. So your voltage gain will still be the same, but your swing will change. So what does this mean? So your signal swing reduces as you add a load. So with output load, signal swing reduces and it is the upswing which reduces. Now what happens if you do say what happens when you do a voltage gain? What happens when the gain you add here? What happens to the gain? Input loading will not affect the gain because no current input, nothing there. So input, no gain impact. By increasing the loading the input, you don't see any impact. But what happens when you load the output? Your gain reduces, right? Because now your RL is now in parallel. You will have R0, parallel with RD, parallel with RL. You'll have three elements in parallel. And you will know that GM times R0 RD by RL is going to be always less than GM times R0 by RD. So your gain will reduce. Why the gain reduces? Intuitively, instead of all the current going through the MOS transistor, some amount of current will go through ID also. So when current goes here, your effective ID reduces. So when ID reduces, GM over ID, though it will increase, but still RL will come, it will go in parallel. So that will also reduce. Now, what are the major limitations? I think with this topic, we will close for today. What are the major limitations of a CS amplifier? First one, major limitation is if you have an increase in AV, if your AV increases, and how do you increase AV? AV can be increased with GM and RD. Okay. If you increase RD, what will happen? IRD will increase. Swing will reduce. Right? So if you increase RD, your swing PD will reduce. Now, what happens when swing reduces? Your VDS reduces. So this limits voltage swing. Right? So if you increase RD if you want to increase the gain by increasing RD, your swing will get limited as your VDS will come smaller. Second, increasing RD is difficult to fabricate because it occupies more area, more chip area. As an area goes up, it is a major constraint because the aim is in more area pack more transistors, or in the given area pack more transistors. If your resistor is taking up more area, the amount of transistor count will come down. This is one. Second, last one, as you try to increase RD is made using poly resistor. Polysilicon will be there. So what is the polysilicon value there? It will come. So, and polysilicon varies with PVT. And typically that number is anywhere between 20 and 25%. So you have an issue with precision. For example, if you are doing a 1K resistor and you have a 20% variation, assuming 10% on each side. So in this case, you have 1.1K. On the other side, you have got 0.9K. This will vary your gain by 10%, or sometimes the current will also go up because your ID will get impacted, VDS will get impacted, swing will get impacted. So you will not have a fixed value. So what you do is the transistor that is present, the resistor that is present, so this is V in, this is VDC, okay, fixed capital VGS. So this is a passive resistor, right, load. Now you will introduce something called active resistor or an active load, which will overcome this problem. Problem is overcome. Now, what are the active loads? There are two kinds of active loads we have seen. First one is, take this resistor, transistor, okay. If you connect the gate and drain, this becomes a diode connected. So this is called a diode connected load. What happens with diode connected load? Diode connected load, the R out of this device is fixed to the GM. So this is called a 1/GM connected load. So your R out will always be 1/GM. Second, you can connect it as a current source. What is current source? You can connect the MOSFET in saturation region. In saturation region. You know, in saturation region that the ID is fixed. So this becomes a current source. So how do you make this as a current source? You bias this appropriately. Drain, source, and gate. You appropriate it, bias. So this is where, here in this case, what is the R out? R out is 1/lambda ID. And in this case, we know that if you compare these two, 1/lambda ID has a higher resistance compared to 1 over Gm. So this is a large resistance device, okay, in saturation. Last one, okay, is going to be in triode, but in triode mode. Okay, if you look at it, this is edge of saturation, where your VGS is always equal to VT. This is in saturation, and this is in triode. Note, you can never use an active load in cutoff region. So cutoff region is ruled out. Okay, so these are the 3 active loads you can do, and this effectively becomes a 2-terminal device. The diode will actually act like a 2-terminal device in this case when you have shorted. So this will be plus, this will be minus. So you can act this. This would be a 2-terminal device, but it will be a gate control. So it is a gate controlled 2-terminal device which allow a fixed current ID to pass through it. Here you will have a diode current ID passing through it, right? So this is a 2-terminal device effectively. So this is how these active loads can work in both as a resistor. Now, if you want to use the graphical understanding, if you want to understand visually how this works, the expectation for a resistor is it has to be linear. Its slope has to be given as I is equal to V by R. So this will be the slope. Now, for which resistor this will work, which load? This will work when it is device is in saturation region. Current source, no, saturation region, linear resistor, not in saturation, triode region. So in the region greater than VT, if your input is greater than VT, till it hits the saturation region of VGS minus VT, right? Till that portion, you can have this resistor, the device operating as a resistor. And this region is always beneficial. So this will reduce the load. So this is called a diode connected load. Understood? So beyond VT, what happens? Beyond VT, the current exponentially increases. So we do not want exponentially increased value there. That is why we can have both resistors and the diode connected load in the linear region. Now, what happens when you do it in a saturation region? So how does this look? How does this passive resistor now look like? This resistor will look like so. Instead of this, now you will have diode connected. So for NMOS, it is diode connected like this. VDD. Here we will have the output. So this is what will be the transformation. This is what it will look from passive connected to active diode. So this is passive load. This is active load. This is VT dependent. There is no VT dependency, right? So this is how a common source amplifier with a diode connected load will be done. Now, instead of this diode connected load, the there is one condition that you will have to understand. Let me draw it visually. So the visually, your equivalent work is for the resistor. This is a resistor for V in, V out. But for a diode, we know till Vt, there is no conduction absolutely. So beyond Vt, the current increases, right? This is diode connected load. So what is the definition that you will see here? Oh, apologies. This is not V out. This is current. The current will shoot up. Okay. So how is the current looking for a resistor? Current is always V by R for a resistor. But for I, current will be for a diode. It will be 0 for Vi less than Vt. Right? And what will happen when the current increases? Right? It is now K times V divided by Vt square, or your Vi. So there is a exponential increase present here. One condition that you can work it. What is a common condition between the resistor and these two? Only this point. When V equal to 0, I equal to 0. So this condition is common to both. Another condition, they have an increasing current. I increases when Vi increases. That much is sure. The rate at which it is increasing is different. Now let us look at how we can tackle that. For Vi greater than Vt. So how do we tackle that increase? That increase can be done is, instead of using this as a resistor, you will get a load line. What is that load line? For a saturation is, the moment you hit this value, your resistor value will be fixed. So what does this look like? Let me draw with a graph. Intuition is important here, because once you get the intuition, you will be able to solve it easily. So if your VDS, this is your output voltage versus your output current, output voltage, output current. So as your output voltage VDS is lower, your I will be high, and as your VDS goes up, your I will reduce. Now this one for a diode becomes, starts from 0. The moment it hits Vt, it will fix and stay there. Now this value of ID and VDD is now your load line, quiescent point for this transistor operation. And this will be where Vt will happen if you want. And this is the point where VDD minus Vt is. So beyond VDD minus Vt, current is 0. So this will be the condition, assuming Vd is here. Now the transfer function of the CS amplifier will still stay the same. What is it? The transfer function of the CS amplifier is expected to be like this. Sorry, it doesn't go to 0. So this is your transfer function. What is the transfer function notated as? Your input by output. So what is the main transistor saturation region? dV out by dV in has to be greater than no, it has to be very large compared to 1. Then only it is called in saturation. Understood? This is going to be the transfer function. Now let us quickly do an example so that whatever we saw today sits down in the head correctly. So I will call this as diode connected load. So this will be, we will do a diode connected load analysis, DC analysis, and see how it works. So how does this work? First thing, what is the DC analysis of the diode load? First, draw the diode load. This is your diode connected device with your V is here, I flowing through this device, positive and negative terminals defined. If V is greater than Vt, then I is given as K times V minus Vt whole square. Now what is V? V is the voltage here. Or you can also define this as V is equal to I by K under root. Take K this side, put it in the root, I by K plus Vt. So you know what is I, what is Vt defined. Next, find out what is Gm. Gm is given as 2K times VGS minus Vt. Or this is rewritten here, 2K times V minus Vt. Next, R naught. What is R naught? 1 over lambda ID. What is lambda ID here? 1 over lambda I. What is I? This equation. 1 over lambda K times V minus Vt the whole square. Right? So this is step 1 is DC analysis. DC analysis. Step 2, find Gm and R naught. Right? Step 3, draw the small signal circuit. What is a small signal circuit here? How does it look like? Very simple, right? Same. Gate, drain, source, T model. Draw the source first. Source. Gate is here. Drain is here. GM VGS. R naught. Okay. We know GM. We know R naught. This is our VGS. Now, one important thing that this is a transistor. How do you make it a diode? Gate, drain connected. That means take from gate, connect to drain. So this is your gate drain connected. What does this mean? The total current is I. I is equal to ID. Now, how do you proceed next? What is the equivalent diagram that we can draw? Tell me. Only re-equate. Now, since gate and drain are shorted, what is G here? No, G is here. S is here. So this VGS can be translated to this node. You can remove this connectivity. So what this becomes? So this is GM VGS and R naught. Now, since the gate and drain are sorted, your VGS is here. So this is plus and this is minus at the source. So the VGS is given here. You have the same GM VGS current flowing through, R not flowing through. So this is the only effective design that you have. Understood? Make life simpler. We'll write VGS inside and GM VGS outside. So VGS is here. This is GM VGS. So a diode connected load will look like a current voltage controlled current source plus R naught in parallel. So this is your VGS. So along with the R naught, you will have a small current source coming in your VGS, right? So that is how it translates to. So wherever you have a diode connected load, you can replace with this effective one. Now let us apply this. Now important is application. CS amplifier with diode connected load. What happens in the CS connected? So the circuit will look as follows. First, the active part, right? You have the active part connected to ground. Now you have the load. How does the load look like? Diode connected. Then the VDD power supply. Now this will be the input. What will be the input here? VI plus DC voltage VGG or VGS, right? This is VI of T. Now what will happen in the output? Output is V naught of T. Now that we have two transistors, we need to identify them. So we will identify this as M1. We'll identify this as M2. Both are NMOS devices, right? Now first when you do for this particular circuit, let us find out what is the open circuit voltage gain. What is the voltage gain? What is the input impedance? What is the output impedance or output resistance? So let us find these two. Now we need that. It is a very simple, straightforward, step-by-step approach. First thing is we will do DC analysis. What is the DC analysis? All the DC devices will go to no. All the input sources or small signal sources will become 0. So your circuit effectively becomes this is our large signal analysis. So here you have VG, this is V out, this is VDD. So the current ID2 because it is flowing through M2. This is ID1 because it's flowing through M1. So this is a notation. Note that in this one so we will become the answer. ID1, ID equal to ID2 equal to ID1. Okay. And what is VGS? VG minus 0. So this is VG. Done. We also know now what is VDS. Right? What is VDS? Which VDS? This VGS. This VGS is now shorted here. See that? That gives a different color. VGS is equal to VDS of 2. So VGS2 equal to VDS2. This is important. Finally, last one. So now we have found out VGS1. Okay, this is VGS1 is VGG. VGS1, VGS2, VDS2 is found We need VDS1. What is VDS1? Yes, VDS1 is VDD minus VDS2. So VDS1 is equal to VDD minus VDS2. So this is basically applying KVL in these places. What happens here next? Now this is the basis with which you will start solving the problem. So we have found out VG, VD, ID. What is pending? VGS, M2. We know that diode connected devices are edge of saturation at all times, right? So diode connected edge of saturation, and this one we will enforce saturation. So what is the current equation? Enforce saturation on M1 and M2. So what will be the current equation? ID1, that is for the device. ID1 will be K1 times VGS minus VT whole square. This will be K1 times VGS is VG. VG minus VT the whole square. Next, what is the ID2? ID2 we know for sure saturation because it is edge of saturation greater than V, or VGS is equal to VT and VGS is equal to VDS. So it is always edge of saturation. Same ID current equation will apply. K2 times VGS2 minus VT2. Now we know that these two equations are the same, right? When these two are the same, we can equate. So it will be ID1 equal to ID2. ID1 is equal to K1 times VG minus VT1 whole square, and ID2 is K2 times VGS2 minus VT2 the whole square. What is the other way of writing this equation? Only VGS is brought out here. K1, K2 is a ratio. VG is known. VGS2 is not known. VT is known. So how do you rewrite this? This can be rewritten as, first thing is bring K1 and K2 and remove the square. So they will go under square root. So that will be K1 by K2 under root times VG minus VT1. VG minus VT1 plus VT2. Now this is equal to VGS 1. This is one equation to refer. Next, we know that VGS is equal to VDS2 and VDS1 we can check. Now let us check what is VDS1 and VDS2. VDS2 is equal to VGS2. VDS1 is equal to VDD minus VDS2. Now let's find out the values of VGS1 we have found out. What is VDS1? We will go VDS1 as follows. So VDS2, same VGS formula we can apply, root K1 by K2. So VGS2 equal to VDS2 is equal to root K1 by K2. VG minus VT1 plus VT2. This is VDS2. Now what is VDS1? VDD minus this value. That will be given as VDS1 is equal to VDD minus VDS2. So VDD minus VT2 K2 minus square root of K1 by K2 Vg minus Vt1. Now, is our assumption correct? So if our assumption has to be correct, what do we do? VGS1 greater than VT1. VGS1 greater than VT1 if Vg is greater than VT1. So that will be good. Right? So this is taken care of. So if Vg, this value is greater than Vt, then our assumption is correct. We are in the saturation region. Now let us find out the two variables that we generally find out, Gm and R0. Gm1 is equal to K terms 2K times 2K1 Vg minus Vt1. Gm2 is equal to 2K2 Vgs2 minus Vt2. Next R0. R0 is equal to 1 over lambda 1 id1, or you can write it as 1 over lambda 1 id. R0 is equal to lambda 2 by id2, or you can write it as 1 over lambda 2 by id. So you have found out GMs and R0s of both. Next, find out what is the total gain. We will identify what is the small signal circuit. This is important. Small signal circuit of CS amplifier plus diode load. What does this look? First of all, find out what is this. How does a small signal amplifier look like? Till now we have done DC. Now if you do AC, you've got two NMOS devices, source load. So here you will remove the DC load, put only the AC load. This is VI. And here there is diode connected, and this will stay diode connected. The VDD can now be grounded. And here is your V out of T. So what is the small signal analysis equivalent? Now remember, you have the small signal equivalent of this device is GM-VGS R0. So this is your G, S, G comma D. Right? This is the transfer. Now for this device, again the 3-terminal device. What is it? Gate, drain, source plus VGS. Mechanically you can go writing this without thinking. Later on you can fill up the blanks. Now what is VGS here? VGS is VIT. Vi of T. No resistor here. So whatever you apply at Vi of T is your VGS you will apply. Right? Then this is your GM-VGS. This is V out. Here this is V out. This is your source. This is grounded. This source is not grounded. Okay, you should leave it hanging. This gate and drain now connected to here. Now if you merge these two, you will get your Vi of T grounded, then VGS plus minus VGS, GM-VGS on the output side, R0. This is V out. Now that V out is there, connect the source here. Connect these two here. GM2 VGS2. So GM1 VGS1, R01, R02. This is your VGS2. This is again grounded. Right? Now, since this is common node and this is connected grounded, you can rewrite this as GM1 VGS1 R01 is grounded. Now from this node V0 to ground. So the current will change direction. GM2 VGS2 to the ground, and there is R0, R02. So this is your effective V out. Clear? This is the important. Now what is pending here? VGS2 is here itself. This will be minus, this will be plus. So this is your VGS2. Here is your VGS1. This is your VGS1. V in of t, the V out of t. So now that you have drawn this, this is your correct value. So this is your small signal equivalent. Now, if you simplify this, how does it simplify for you? Now, if you simplify it, you will merge these two. So you will merge these two, and they will become GM1 VGS1 plus minus, direction is opposite, GM2 VGS2. Then these two resistors will be in parallel. So that will be R01 parallel with R02. So this is the effective GM. GM effective. This will be R not effective. So GM effective, R not effective, same VGS is applied over here. Now, how do we replace VGS1 and VGS2 to fulfill the next criterion? Now for that, you have to find out what is VGS1 and VGS2. Now, what is VGS1? VGS1 is Vin. VGS1 is Vin. That is from here. This is your VGS1 is equal to Vi of t. VGS out is actually your V0, right? So your VGS2 is V0. Is it V0? Minus V0, inverted direction, right? Minus plus. So it is minus V0. So now you know VGS, we can replace this VGS1 by V in. We can replace VGS2 by V out. So you will have GM1, V in, GM2, V out, R01, R02. So these are the terminals that you have. So let us replace them. So what is V out? V out is equal to GM R out VGS1 with a negative sign. So that would be negative sign because of the inversion. Then GM effective multiplied by R out effective, R out prime. If you rewrite this minus GM1 VGS1 minus GM2 VGS2 times R01 parallel with RO2. Right? Now let us replace VGS1 and VGS2 with these two values. So it will be minus GM1 V input minus GM2 V output times R1 parallel with R02. This is equal to V0. Now if you rearrange, you will get the gain. AV is equal to V0 by Vin. So take V0 that side, so it will be minus into minus plus. So V0 will be 1 minus or 1 plus. V out will be plus. Here it's plus. When it goes that side, it will be 1 minus GM2 V0 times R01 parallel with R02. And then whatever is left over will be Vin. So it will be minus GM1 Vi times R01 by R02. You divide these two, the minus signs get cancelled, and you will get 1 minus sign pending. What is that? Minus R01 parallel with R02. I have retained minus and R01 here, multiplied with the GM because it is the V1 factor. G1 divided by 1 plus R01 times this 1 plus R01 parallel with R02 times GM. Sorry, this is GM2, second one. So this can be written as under two conditions. One, assuming R01 parallel with R02 is very large compared to 1, then R01 parallel with R02 times GM will be very large, equal to 1. Then this denominator effectively becomes R01 parallel with R02 times GM2. Numerator we will have R01 parallel with R02 times GM1. So this effectively becomes minus GM1 by GM2. Right? Now this can be written as GM1 over GM2. If you replace GM1 as 2 times root K1 times ID, you will effectively get this as mu n Cox W by L, K1 by K2. GM is effectively now equal to K1 by K2. And the moment it is K1 by K2, you are now only limited by W1 by WL by 2. Right? Now if you see this gain of this transistor or this gain of this AV load can be written as minus GM1 by GM2 or square root of minus W by L by 1 minus W by L by 2. That means the gain of this common source amplifier and diode connected load is only decided by the geometry of the device. Right? W by L over W by 2, you have now full control. You are not process dependent now. The dependence of the process has been taken away for the gain factor. So that is an interesting information that you will use in your circuit design knowledge. So whenever you have a common source amplifier with a diode connected load, you are not dependent, your gain is not dependent on the process parameter. It is dependent only on the ratio of the GM or the ratio of the geometry of each of these devices. Now, here you will have to understand that saturation. One is weak saturation, one is strong saturation. So your diode is weak in saturation. Your transistor is strong in saturation. So in that case, W by L1, in this case, this is M2, this is M1. M1 is strong saturation, M2 is weak saturation. So this will be a strong device, weak device, and it will give you high gain. So strong device over weak device, you get a high gain. Now, what else is information pending? We have found out gain. Our aim was to find gain, input impedance, and output impedance. For that, let us reuse this structure. So what will happen? When you reuse this structure, you need to find out R in, R out. How do you determine them? What is R in? R in is the effective resistance seen here. This is R in. What is R out? R out is the effective resistance seen here. Very simple to follow. Now let us understand what is what. What is the current here? IG, right? So nothing can go into the gate. So R in is V in by I in. I in is 0. So V in by 0 is infinity. So R in is infinite. Now, what is the R out? You can do a mathematical calculation, but here is when diagrams help. This is here R out. You can start it by giving a test input, give it here what is happening, find out what is the test input that is given here. You can do. Send a Vx and Ix. Okay, apply a test voltage, find what is the current that is coming effectively, find out what is the output resistance that is coming effectively. You will get what you will get here. What is the current? Let us do this. Current is GM1 VGS1 minus GM1 GM2 VGS2. So your Ix is going to be this one, but in the opposite direction. So it is negative, right? So what is Vx? Vx is this multiplied by the R out. So here we already found you will get the R out in a very simple manner, that R1 is parallel with R2. Right? Anything, any doubt here? So this will be your open circuit gain. So your R out is going to be R1 parallel with R2. Rn is going to be infinity. So this is the benefit of doing a good small signal diagram. The moment you have a good small signal diagram, your understanding will be extremely simple. Answers will pop out automatically. You will not have to spend more time. Now, there is one condition that you have to look for. What is that condition? There is also going to be a GMB, bulk, right? In ideal conditions. In ideal conditions, you will have a bulk device. Now, what is that bulk device given as? Diode connected load and VDS. So this is your input. This is your diode connected load, VDD.
Sir.
Hello.
Sir, actually it's already like 37 past our lunch timings and the mess will be closed by 1.
Mess will close by 1. Okay, I will close in another 2 minutes because your Tuesday class people did not join, right? So I had to complete this. So let me complete this and then we will take a break. It will take me
Okay,
this to
sir.
1. So V in, I'll be fast, V out. So for the diode connected load, your RD will be given as 1 over GM2 plus GMB2. Why GMB2? Here your bulk is connected to VSS. Here your bulk is connected to V out. So there is a non-zero value. So this non-zero value is captured as GMB. Effectively, your gain will get impacted as minus GMRD. You will get it as minus GM1 times RD is 1 over GM2 plus GMB2. This value is given as AV is equal to minus GM1 by GM2 times 1 over 1 plus eta, where eta is defined as GMB2 over GM2. So when you have a non-zero V bulk connection, where V bulk is not connected to the lower device, so if there is a VBS and this VBS is greater than 0, you will have to consider the GMB2 in your resistance. So your effective resistance will be GMB2 plus 1 over GM2 times GMB2, and that ratio is brought out here. So this is the impact of bulk in your gain factor. So your gain is easily given as minus GM1 by GM2, which is times this ratio 1 over 1 plus eta. Now if eta is very small, effectively this will be same as minus 1 over GM times GM2. And you have to keep this small to ensure that your ID value is constant. That ensures your GM will be constant and your input-output relationship will be linear. So, okay, with this, thank you. I will now stop, and please turn on your cameras for the customary photograph before we leave the session today.